Okay, we're going to get started. This is the day after the exam, so if you're watching videos and you're not part of the UCCS community, I did give an hour exam on Tuesday. And there are people watching from other locations that just tell me that they like the videos and they appreciate the free videos. So I'll leave the old video up for Tuesday from a year ago, and then there'll be one for Thursday this week. The first thing I'm going to do is pass around some breadboards that go along with the lab. Some of you are in the lab, and yesterday you started working with the receivers, right? The radios?
It's probably the best lab yet because we were able to finish it in a period.
Well, I told you it was going to be fun lab and an easy lab because all the hardware was built, but you still have to take measurements and know what you're doing. But hopefully the frequency translation idea became extra apparent after working on those radios. But I thought what I'd do is I'd pass around when I developed those radio modules that Professor Teekamp did the PCB design for. These are what my original breadboards looked like, RF breadboards that I constructed the circuits on. This has got a surface mount part on it that I had mounted at Spectrum Laser, which those of you in senior design, if you haven't heard about Spectrum Laser, you want to go there to have them assemble your PCB. So I had them just put these surface mount chips on there on a header, a breakout board that could go into a dip socket, and then this RF breadboard is got a checkerboard on the top, and then it's got solid ground plane on the back, and it's got vias that aren't plated through, but you can pass a wire from the top to the back, so you can, in a sense, get your ground very, very short RF-wise. This is the single conversion radio. And because I'm on my mic, I'll pass it over. This is the dual conversion, so it's got the crystal on it to act as the second local oscillator. These are both FM receivers, so there's an extra inductor besides ceramic IF filters. There's an extra tuned inductor in a metal can on this one and on the other board that act as the frequency discriminator, and we'll be talking about discriminators in Chapter 4. Discriminator is the term used for demodulating FM. It discriminates between one frequency and another. It almost seems like to say the word discriminator is bad in our vocabulary today. Discrimination is a bad word, but I don't think it necessarily is at all. I wish we had more of it on this campus, namely for faculty and staff to have parking that was our own parking, so we could actually have a place to park and not spend $700 and not even have a parking space. But that's been a bone I've picked for decades. Those of you that have not gone to school at another campus don't realize how good it is here. You pay a lot of money, but at least you get to vie for parking. And other campuses that I went to, they were real campuses, and they had parking for faculty and staff. And Boulder, I think, actually has that too. But at any rate, I shouldn't be ranting too much because you'll write me up for it, but just understand that it's just one of those things. Okay, so the project is up there, and we're going to spend some time talking about it. I want to actually get into that after I kind of get a little bit further down the pike in closing out Chapter 3. So there's a project reader, and then there's a Jupyter Notebook, which I've reposted, unfortunately, many times because I'm trying to get all the text to sync with what's in the PDF. So I reposted it. Last time I reposted the notebook was at 10 p.m. last night. And I probably posted it about 5 different times because I keep looking at things that I've tweaked on it and getting it to all track. So what we want to take a look at to kind of clear the way to the next phase of Chapter 3 is we have just a little bit to do in interference modeling. And this will get revisited in Chapter 4 for angle modulation. But interference modeling for linear modulation, as in double sideband or AM or single sideband, all very similar in terms of the modeling. This picture is depicting what type of modulation, though? If you see a spectrum picture that looks like that, just suppose this is not there. What does that spectrum look like? Well, it's double sideband, but it's double sideband plus carrier, which would make it AM then, right? Double sideband would just have the upper and the lower, but there's a spike in the middle. That's the carrier, right? So you can do envelope detection on it. But I mean, that's kind of, and this would be a single tone message, just a test message. So now what we're going to be considering is what that red spectral line is sitting out there at some frequency f sub I offset from the carrier in an amplitude a sub I. And this is shown as a single-sided spectrum. So that would be interference or jamming. So what gets added in now in the model is we're going to add in the interference term, and we're going to have, in this case, AM modulation, because there's both double sideband, which is this piece right here, and then the peer carrier makes it AM. And then we're going to see what is the impact of that. Well, on the coherent demodulator, we just multiply by the reference, and we downconvert to baseband, put in a low-pass filter, and then our message is recovered right here. But then we have the interference. But the interference may or may not actually be an issue. Right now, I'm assuming that that's prior to, well, it's after the low-pass filter. The double frequency term is gone, but suppose the low-pass filter was narrower than this offset frequency omega I, it would not enter, we would not hear it, right? It would not come out because the low-pass filter would block it. I'm just thinking of what the DMOD would look like. So if there's a low-pass filter in here, we're expecting to see our message coming out over here. But then we also have this f sub I sitting in there. But it might just be that the low-pass filter is going to remove the interference. But needless to say, if the interference is pretty close, it's going to definitely get through, and it's going to be an issue at that point. So with the coherent demodulator, the interference comes riding through. If it's outside the band of interest, the low-pass filter would get rid of it, so that term may be removed. And on the project, you'll get an opportunity to experience that, because if your design is not done properly, you will get interference, and you will hear it, and you will be somewhat annoyed by it. But it'd actually be good if you made a mistake and got some interference, so you at least appreciate what it sounds like. At any rate, for the coherent demodulator, that's pretty straightforward analysis. Now, what about if we were doing AM with envelope detection? So if we were doing AM with envelope detection, we have to go back to that envelope modeling we were doing earlier with the complex envelope. Remember, forming the complete complex signal with the interference coming in terms of the in-phase and quadrature. So this is the in-phase part and the quadrature part of the model. But then expand everything with respect to the carrier, omega C, and look at the complex envelope R tilde. So R tilde is going to have the peer carrier component, which is like a DC bias. It's going to have the message, but then we're going to get these two pieces from the interference, just the expansion into sine and cosine, and then the envelope detector is going to pull off that envelope, which gets us back to where we were before. It's going to be the real part squared plus the imaginary part squared, and assuming AC is very large in this model, we can go back to that binomial expansion idea we were talking about last week. And the dominant term coming out then is going to be the original message and then the interference term. Still, just like the linear coherent or the coherent demodulator, if that interference is above the band, the low-pass filter in the receiver or the envelope detector has a low-pass filter effectively in it, it will also get removed. But it only enters the picture as a linear summing of, a superposition of the desired and the interfering term. And this is a simplification, of course, too, saying it's just a single tone interfere, but it might actually be another radio station jamming that's just nearby, and then it would be some composite signal. But in this case, we're using just tone interference and tone modulation just as a simplifying case. And maybe that's a time to pause for a second. Does anybody have a problem with that? Just to check ideas out? Put in a single tone, should get a single tone out. Have a jammer that's a single tone. It's going to come out as a whistle or some annoying whistling sound at a high frequency. And if it goes away, it's gone. If it's too high frequency, it's totally gone for two reasons. Number one, it's above our hearing. If it was audio, if it was digital, it would still be causing harm. But if it's outside the bandwidth of the low-pass filter, then it truly is mitigated. So using the sinusoids is just to keep things easy, and then you could progress to a more exotic model. And you're going to do, in this project 1, you're going to first test with noise using a noise model representing a full bandwidth of the signal or the message that's been shaped by a low-pass filter, and that's going to represent the message. And then you'll carry that all the way through in simulation, and then you'll replace it with speech. And I'll be demoing that in a little bit here. For the envelope detector, though, if the interfering term becomes large, so AI is much greater than AC, it's like you get a long ways away from the AM signal of interest, and you get close to a jamming signal, or an interfering signal. Then if you go through the detector analysis, I'm going to draw a spectral picture out here. So the green ones represent the upper and lower side bands of the tone modulation or tone message and the carrier. And then the interfering signal is very large in amplitude, and it's sitting at an offset of Fi from Fc. So the envelope detector, and this is a really neat concept to think about. When we looked at the envelope detector for single sideband, remember we re-injected a carrier when we looked at envelope detection. We re-injected a carrier, and nominally you re-inject the carrier where there is no carrier, right at Fc for single sideband, and then that injected carrier acted like a synthetic carrier that wasn't perfectly on frequency, but still, remember, when we listen to it, it sounds not too bad. It sounds fairly decent. So now, thinking of that idea, the carrier that's in blue, Fc plus Fi, it looks like the components down here look like lower single sideband terms, just with respect to this strong interfering tone. So what is the envelope detector going to recover? It's going to recover those three tones, but as the model up here shows, they're going to be offset by this interference frequency, omega I plus omega m and omega I minus omega m. So the big emphasis that Dr. Ziemer has in the book is the message is lost, because the frequencies of the message, if it was speech, is just like shifted way off in frequency, and it's just gibberish at that point. It's just nonsense. Does that make sense? The interference just looks like the real carrier, and the envelope detector says, I can't tell the difference. It looks like we have a bunch of, the real signal looks like lower single sideband, and everything gets referenced to the jamming signal. And if the jammer moves around in frequency, the message up above here gets shifted up and down in frequency, and it's like, it makes no sense. Has anybody ever listened to a radio where you're trying to tune in a station and you just hear things that are kind of like a signal, but you can't, there's no intelligibility, it's maybe a whistling sound if it's a steady carrier? And then there's some other components that you know have the message inside of them, but you can't, they're not intelligible. I mean, what would happen here is that this would come out, and that's just going to be a pure tone because it's the shifted version of the carrier that was on the original AM signal. So that would be a strong whistle at a fairly high audible frequency, let's say. And then the other two terms would be, rather than a single tone message, would be something to do with the modulation. So you'd hear sort of a superposition of all three of those. At any rate, you can't mitigate it at this point. The only thing we could do to mitigate the interference is at the input to the demodulator, we'd have to do what? Put up a bandpass filter, right? And if the jammer wants to climb right into that bandpass filter by having their signal right on top of you, then what? Do you give up? You could use a notch filter, that's what I was going to say. So yes, you could use an adaptive notch filter, and adaptive signal processing can come along using an adaptive notch filter. And actually, there's a technique that relies upon digital signal processing techniques in the fast Fourier transform where you can do real-time processing in the frequency domain. So in the frequency domain, if you FFT the received signal that has the interference in it, you can just go scanning across all the bins or all the frequency points in the FFT and look for one that looks suspiciously large and like it doesn't belong here. And then you can null that single bin out and then inverse FFT and get your signal back to a certain extent. It's not going to be quite as perfect, but it's adaptive nulling is what it's called. So it is a technique for mitigating jamming to a certain extent. I say to a certain extent because it can be very, very effective, but if somebody really wants to overpower, it's like arm wrestling. They could really beat you up badly if they want to, because they can just turn up the intensity. But see, Steve is one who sits there, right?
Mike.
Or Mike, yeah, I've got the names mixed up. I was talking to him after class because he was in the Army and worked in radios and comms, and when people are battery powered and other things, the interferers are limited in how much power they can produce. And then he made mention of the fact that if they're really powerful, you can also geolocate them very easily. And then what do? You can take them out, right? Just say, we're going to make you cease and desist by destroying your transmitter. Interference isn't always intentional, though, so we also have that scenario where it's just you're driving past a radio transmitter, your receiver is not really selective enough with its front-end filter, and it just plain leaks in and kind of destroys it. Now, I don't know if, has anybody ever had that happen? They drove past a facility and their radio temporarily went bonkers and then it returned as soon as they went away. Has anybody had that happen? Because they're yeah, power lines definitely do it. They give that buzz that you hear. And that's kind of the same idea when you're, since my family likes to listen to baseball, we were heading out listening to KOA from Denver, the Rockies station, and we were going to Kansas, Wichita, where my son is living right now. And AM radio does not have a thresholding effect. We'll learn about that later. It just gradually gets weaker and weaker. The noise becomes more noticeable. FM has a thresholding effect. And all of you, I'm sure, have experienced that. You drive over Monument Hill, what happens? Stations are gone, and then you start to get the Denver stations, and then it gets schizophrenic a little bit, where you get some of each, flip-flops, and then pretty soon it's just all the Denver stations. But AM just gradually fades away. So, yeah, when we get really way out there on I-70, you go underneath some high voltage lines and you hear that bzzz, because that's kind of the interference that's coming into the radio at that point, because the AM station is so much weaker. Where I had it happen when I was growing up, though, is, and we have it here in Colorado area, the AM stations that have their directional antennas are out from the Front Range, and if you would be driving on a county road or something out where the antennas are for the AM radio stations, because they're not on Cheyenne Mountain, and you went past the antenna farm, I might call it a mini farm because it's got maybe 5 monopoles. They're like dipoles because of the ground plane effect, but those form a phased array so that you have a linear array of vertical monopoles that are phased so that all the AM radio energy points into the city and doesn't point omni because they don't want to point it where there's no population. They want to put all their punch power where the population is that's going to hear the ads, and that all makes sense, doesn't it? And electrical engineers always help, right? We're going to design something to make you do what you want to do. At any rate, driving past one of those things would generally overload an AM radio in a car. It would just sort of take it out for a little while, and then as soon as you're past, it would come back again. Okay, that's the end of that, and we will revisit that idea of interference. So the main takeaway at this point is if it's a coherent demodulator, the jammer just superimposes on top of the original signal. The filter might take it out, but you know, it doesn't cause dramatic effects. If it's not too strong with an envelope detector, it acts kind of like the coherent demodulator. It's just superimposes. But if it's really powerful in a envelope detector, then it wipes everything out. It's gone. So the next topic is sampling theory, and there's some neat demos in the homework, in the Jupyter Notebook, and then there's some problems you have in the homework on sampling theory. So I'm going to take this down a little ways, and then I'm going to jump to the project. So sampling theory is something you've seen since 2610. It was refined, I believe, in 3205 when you saw the Fourier transform, but in case you don't remember that, or maybe Dr. Trimboli doesn't do sampling theorem in the Fourier domain, because I don't know whether he does or not. Do you know?
Yeah, he did that.
Okay. So when you have Fourier theory, and we've of course reviewed it here, we have the sampled signal spectrum, or the sampled signal is on the left there, x delta, and then what you do in sampling theory is you say, okay, the delta samples are the ideal opening and closing of a switch, so this is your this is your continuous time signal with its samples, but then we later say that actually gets fed into an A to D converter, and we're going to get digital words to represent each of those samples, but just momentarily passing through the idea of sampling a continuous time signal at discrete sampling points uniformly taken along the time axis, we come up with the low-pass sampling theorem that says that as long as you sample at greater than twice the highest frequency, which is W in this case, you can reconstruct the signal from its samples. And then there's a couple of definitions that go along with sampling theory. 2 times W is known as the Nyquist frequency. That's the frequency that you have to exceed if you want to successfully sample and recover using low-pass sampling ideas. And then Fs over 2 is half the sampling frequency. That's also called the folding frequency. The proof of it lies in the ability to use a theorem from Fourier transforms, and that is multiplication in time is convolution in frequency. So we convolve the spectrum of the ideal sampling waveform, which is this, with the spectrum of the message, and then that convolution is the easy convolution involving deltas, so it just replicates the spectrum up and down the frequency axis. So you end up with this picture that you've seen before. You have the spectrum at baseband, and then you sample it, and you end up with images at multiples of Fs, all the positive multiples, all the negative multiples. And as long as you can see the original baseband spectrum sitting out in here, and it's not touching the nearest neighbor spectral images, you can come in with a filter and pluck it back out of there by just visualizing the action of a filter, right? Multiplying the frequency response by the spectrum, and then you can recover the message. If you're not sampling at greater than twice the highest frequency, then you get some overlap. And that's the aliasing idea. And aliasing is, I don't know, has anybody ever looked up aliasing on Wikipedia or in the dictionary? When I have taught 2610, I've oftentimes looked that up because aliasing is so prevalent in our world today, especially for engineers. We have aliases in Python, for example. When we say import something as some other name, that's an alias. We have aliases in operating systems. We have aliasing in sampling theory, and then in real life we have aliasing too, right? I mean, I was hearing on the news yesterday that our president maybe has different aliases that he's used in different things, and of course criminals frequently use aliases, right? They don't want to use their real names, so they have aliases. But if you look up in the dictionary aliasing, you find those common examples, but usually they talk about sampling and some electrical engineering related idea. They generally don't talk about aliases in operating systems and in programming languages, but they do talk about sampling theory. They try to include that. I don't know what you think of that, but I think it's kind of cool that we rank high enough to show up in a Webster's definition of aliasing. Maybe not clearly explained, but at least it's part of an engineering terminology that makes sense. So aliasing is a permanent thing. Once you do it, once you commit aliasing in a signal processing application, you cannot, without a priori information, remove it. It's polluted your system. The aliases are there. As long as you're not aliasing, though, this section in the notes just says you can come along with the reconstruction filter, and the simplest reconstruction filter is just the ideal rectangular brick wall filter, bandwidth 2B, so it's got ones from minus B to plus B, so a low pass bandwidth of B, and then this is just to say linear phase, so it's distortionless over the band of interest. And if you back that out, you've just got, if the signal is perfectly band limited, which is not physically possible for signals of interest. Why is that again? Remember we talked about that spectral inverse spreading idea. That was the end of chapter 2. Inverse spectral spreading says only signals of infinite time duration can have finite bandwidth. And signals that have got time limited duration have infinite bandwidth in theory. And the extremes are a DC from a power supply only has a spectrum, it's a delta function, so that's very band limited, whereas a signal that's a delta in the time domain has a constant spectrum, so it's very broadband. I think that's a worthy concept to keep in your mind. So short-lived signals take lots of bandwidth, long-lived signals are narrow in their spectral occupancy. At any rate, if you write that out using the inverse Fourier transform of the rectangular function, you see that the ideal interpolation function to reconstruct from samples would be the sinc function. So the sinc function is the ideal interpolator, and you take samples from your underlying signal to do that. So I don't have a picture here in the notes, but I think you've seen this picture probably a few times in your life. So suppose those are the samples on the time axis. So now you've taken your samples, put them back on the time axis. Samples would have been residing, say, in the computer as just digital words, and then you come along with your sinc functions, and the sinc function is going to come along I'm not drawing this super accurately because I'm not usually doing a picture like this. At any rate, the idea is if you superimpose all of these guys right in this area, you will get back all your signal samples will eventually construct into, the original waveform. Maybe you did that in 2610 as a homework problem or something. Just showed that you could take this equation up here, take a waveform, sample it, and then try to put it back together again by taking just the sample values, and at each sample value location put a time-shifted sinc function and then superimpose all of them, and you get back what you started with. It's really easy to do in the Python Jupyter Notebook too. I don't know, do you need convincing? I remember one occasion a long time ago when I was with another faculty member teaching a DSP short course, and somebody said they don't believe in the sampling theorem. It's just not true. So they argued. We argued about it for a while. I wasn't the professor teaching that part of the class, but somebody that I taught with here who's no longer here had to handle that question by somebody saying, it doesn't true, it doesn't work. So. I think it's good to be convinced of it, though. So another part of the sampling theory, and I'm going to come back to that and give you a couple demos here. Another part of it that's new is bandpass signals. And I've given you a special problem on the homework that you're going to investigate the idea for bandpass signals for software-defined radio. So I decided to push the envelope just a little bit this time and see what you guys can make of this problem, and just see how a software-defined radio front end can get by with bandpass sampling. So the idea with bandpass sampling is your signal doesn't occupy a low-pass bandwidth, it occupies a bandpass bandwidth, and the notion is that you don't have to sample at greater than twice the highest frequency. You can get by with a lower frequency according to a theorem. And the theorem that's here in the notes in the book is that f sub s, rather than having to be twice the highest frequency, which is fu, f sub upper is what that stands for. Nominally, in low-pass sampling theorem, you take fs has to be greater than 2 times what would be called f upper. But now we can divide it by m, an integer, and it's the greatest integer less than or equal to the upper frequency fu divided by w, the bandwidth of the signal. That's the idea of the bandpass sampling theorem. So this is an example that's in the book, I believe. So it's a signal that just has a bandwidth that runs from 2 to 4 hertz. The f upper is 4 hertz. Plug it into this equation. F upper 4 divided by w, which is 2, and you get 2. So m is equal to 2. So fs equaling 4 actually works for this signal, rather than what would it nominally be for low-pass sampling? Twice f upper, so instead of 8. So if you put it together, this is what the spectrum looks like of the sampled signal. If you undersample it relative to the low-pass sampling theorem, you get this is the sampled signal spectrum. And the notable feature right here is that you have images inside this interval 0 to fu. And normally you'd say, that's no good. But because we're talking about a bandpass signal, the way you recover the bandpass signal from its samples is with a bandpass filter. So you can see from the picture there that if you put a bandpass filter around the red triangles, which is what the original signal spectrum was before it was sampled, you've got it back again. Does that make sense or sound reasonable? It's not breaking sampling theory, because this is now the bandpass version of sampling theory. So software-defined radio takes this even further, and I'm going to be showing you a demo of that next, by saying, look, I can sample a signal, and as a result of sampling, I will get it digitized into the discrete time domain, and I'll also be able to frequency translate the signal, kind of like you'd want to do in a receiver. So in this case, we can see that the original signal spectrum got moved down to here, And taking this to an extreme, it might be in a radio system front end where there's, and this is the scenario in the homework problem. The IF signal, which might be 70 megahertz, 140 megahertz, or some high frequency, or 10.7 I put in the homework. By sampling this signal with an A to D converter that can process a bandwidth much above the sampling frequency, and you have to have a special type of converter to do this. It's generally called either a flash converter or a successful approximation converter would also work. You're going to purposefully sample at less than FIF. You're going to sample at a much lower frequency, and you'll end up with translates filling in, and I'm going to show this as an animation in a second. So what happens is with your sampling operation, you actually take the spectrum and you shift it down in frequency, which is what a receiver has to do. You get it digitized, and then a very popular thing to do is to get the signal be centered on 1/4 of the sampling rate. And once you have it at 1/4 of the sampling rate, then you can have it in then it's in the DSP domain, and you can do complex frequency shifting on that, and you have to just shift it so it's centered at 0 or baseband. And the FS/4 is a magic frequency, because to do the e to the j 2 pi f naught over fs, where f naught is FS/4, turns out to not involve any real multiplications. You end up with multiplying by 0, +1, or -1. I'm not really going into details on that a lot. It's something I cover in modern DSP, but needless to say, it's very easy to then translate it down, and then you can reduce the sampling rate by a factor of 2, and then you're good to go at that point. So it's a nice way. It's a cute way. It's also known as IF sampling. It's another name for it. But one of the assumptions, though, in all of this, though, if you're going to do this, is you have to be able to have your front-end signal pass through a bandpass filter that's pretty narrow to make sure that nothing either side of that is going to get aliased down, because otherwise it's kind of like an accordion. All these other bands, when you undersample, are going to fold down and land on top of each other and stack up noise or interference. But assuming you have a nice tight filter, like an IF filter in a receiver, then you can reject the adjacent signals, then you can undersample in A to D and translate all in one step. So let me run a demo to kind of make that more concrete. When I wrote my dummies book, I had some software that I wrote for it using a language called Zojo, which is a cross-platform development environment for GUI apps. So the first one I'm going to show you is just a review of sampling theory. This is just a plot of a sinusoid in red, and I'm assuming that the sampling rate is 1 hertz, and then with this slider I can change the frequency of Fs. So I can change, Fs is equal to 1 hertz. I'm going to change the frequency of the sinusoid. So as I do this, you can see as I increase the frequency of the signal, what starts happening, I have less samples per cycle, and eventually I reach a point as I move along here where I have what? I have 2 samples per cycle. So why does the sampling theorem say that you have to sample at greater than twice the highest frequency? This is like a little trick. If I sample at exactly twice the highest frequency, like of this single sinusoid, I've got samples at the 2 peaks, but if the signal is phased, and I'm going to change the phase of the sinusoid, what can happen?
You get the wrong signal out of that.
Or you get nothing. This is what I think the guy many years ago was arguing about why sampling theory doesn't work. Because if you sample it exactly twice the highest frequency and the phasing is wrong, you get nothing. But what are the chances of doing that?
Well, the Nyquist theorem also specifically states that it's greater than
Yeah,
twice the highest frequency.
yeah, that's true as well. But if you wanted to drive it to the limit, though, why can't I be exactly equal? Well, the nature of this is as long as you're asynchronous, the two clocks, the sampling rate clock and the signal coming in, are probably going to be slipping past each other just a little bit, and you will get something. You won't see it as that extreme. So now if I keep raising the frequency, eventually your eye starts to see something. It'll happen sooner or later, but eventually you start seeing what? As I keep going up here. Let me know.
Start seeing folding.
You should start to see aliasing. I'm seeing it pretty clearly right there. If I drive it all the way, though, you can see the blue dots are the samples, and now I'm seeing the alias, right? And if I take it all the way, then I'm at DC, just like I started with it at DC. Whereas in reality, if I click this button, it's going to go like this, and then when it hits the halfway point, it starts to go down in frequency from the samples, because that's the principal alias, something you saw in sampling theory, right? It's just a cute little demo thing that I made up years and years ago. Good enough? You can find it on the website under the Dummies book area. This one is the spectrum view. So here, this slider is changing the sampling rate normalized by the bandwidth of the signal. So if I set this at 2, that ratio at 2, I'm just going to meet the low-pass sampling theorem requirement. The blue is what I start with, and these are translates, which you could picture going off either side. But I can recover this. Typically, you'd run with a sampling rate somewhat greater so that you have a guard band that you can have a realizable filter recover the blue one with. But now, next I'm going to consider is bandpass sampling. So I have two other tabs over here. Suppose I have a bandpass signal, the blue one, and I'm sampling at greater than twice the highest frequency, but we were just talking about the bandpass sampling theorem. So now I can just animate that. I will take the slider and move it to the left, so I lower the sampling rate. And as soon as I lower it, I get a translate that's clobbering line of interest, but then if I bring it far enough down, notice there I have a clear patch where I can recover the blue. Keep going. Have a long clear patch where I can recover. Then I get another aliasing event occurring. Then it clears up again. Keep going. Clears up again. And then in the limit, if I go all the way down to here, like that, that's the lowest I can go. And this is not very practical because it's like I have no bandwidth to recover the signal from. But in the idea of the IF sampling that I was talking about, it might be that this picture right in here might be the solution, and this is kind of what the homework problem is dealing with, that I don't want to process the blue signal. Instead, I'm going to process the one that's sitting right here, and I'd make the center frequency on this one be 1/4 the sampling rate. Or maybe I'd give myself some more breathing space and I'd go with this solution. So I'd set this to be 1/4 the sampling rate, and then I would frequency translate that in the end. And that's kind of the software radio processing technique. So I'm having you explore that, and I give you the equations that you're working with. As a hint on that problem, you're probably going to have to do some iterating because it's not really obvious. So you're going to have to iterate on it a bit to get the answer to come out right. And then I have a tool in the Jupyter Notebook that can plot the sampled signal spectrum, and you can see if it's a good result or not, because if it's not, you'll see you'll see stuff like this where there's collisions in the spectral pieces. You're looking for a solution that's where it's clear. Sound intriguing? I guarantee you the companies I work for, RT Logic, Emergent, and Cosmic AES, probably Harris, all these other companies that are working with software-defined radio front ends definitely do this undersampling technique, because you don't want to have to run your A to D at such a high frequency. You run it at a much lower sampling rate, and then you just let the aliasing be controlled aliasing, and then you can do what you need to do with your COM waveform. Any questions? I'm sure you'll have some questions on the homework, but we'll have next Tuesday to talk about that. Okay. So the next thing we go into, and I'm going to talk about the project here for a while, but I'm just going to give you a quick overview. Analog pulse modulation, of which there's pulse amplitude modulation, there is pulse width modulation. How many of you have heard of PWM before? It's very popular in servos and motor control, right? There's pulse position modulation, there's delta modulation, and then lastly there's pulse code modulation, which is what A to D converters do. So we'll spend probably more time talking about pulse code modulation, because some of the other pulse modulation schemes are kind of not too popular anymore. There's a newer one out, or at least a newer name that I just read about recently, called pulse density modulation, and that's what oversampling A to Ds and D to As effectively are using. So they've given it a name called pulse density. And if you've heard of Class D audio amplifiers, it kind of falls into that same category. Does anybody have a Class D power amplifier for their stereo? Ever heard of Class D? Okay, very efficient. So we'll spend more time on that, and I've got some nice tools in the Jupyter Notebook for encoding and decoding, and you'll probably be using that stuff in Project 2, which is a ways off yet. So let's go over and introduce the project. So this is the project, and if you go to the website, just to let you know where I'm at, I'm under Python projects, and I'm looking at the PDF that's linked right in here. And then there's the Jupyter Notebook, which has the audio files in it, some figures, and the notebook itself when you download that zip package. So first off, there's an honor code on this, and that honor code is to just make things fair. And the idea is that teams do not talk to other teams about specific design and implementation details. You ask me questions, email me questions. It's kind of like if you were working for a company that was developing a product that another company right next door to you was developing. You don't want to share what you're doing. You want to keep it to yourself. You just want to do your own development work. I'm allowing undergraduate teams to be at most 3 members. If you're a graduate student, you work by yourself. And you don't share your ideas with anybody either. So this is very reasonable, and it's been very reasonable. I encourage the 4625 students to work in teams. In my mind, I can visualize a few teams already just looking around the classroom. I know who's got their alliances and so on and so forth. So that's fine. I don't encourage one person to do all the work. I want you to really work in teams and share ideas in your team, and then come to me with questions. The due date is noon on the Friday before spring break. I could put it at midnight, but I don't think that's realistic, because I think you're going to be wanting to be off the campus long before midnight on Friday before spring break. What's that?
You could
I'll be here all spring break.
Okay, well, some of us will be here. The worst case for me is I will be in Wisconsin because things have gone downhill faster. I don't know right now what's going to happen. The last spring break where I went somewhere was a long time ago when my sons were in high school. We went down to Tucson to watch the Rockies preseason. But now if you follow the Rockies, where do they play now for their preseason? Scottsdale, right? Scottsdale, Arizona. So it's up in the Phoenix area. It was fun in its own special way. If you've ever been to Phoenix or Tucson, you're not missing a whole lot if you've never been there, but it's a hot place in the summertime. Very, very hot. That's where I work. Over 100 degrees at 8 in the morning, pretty much every day in the summer. Okay, so there's a lot of words here to read, but I'm just going to look at some pictures. This is the basic block diagram of your system that you're going to be building. It's a multi-carrier single sideband system, and just for added realism, there's just 3 carriers that you're going to, 3 carrier-based signals you're going to synthesize and pretend that they're traversing a radio channel, and then you're going to build a demodulator that's going to coherently demodulate one of the 3, and there's a framework for that. The elements that you're going to be building now, you're going to build the generic SSB modulator as Weaver's modulator. You're going to build a coherent demodulator, and then you're going to have to add a few pieces in, like you'll have to design this bandpass filter as well. And it's all going to be done in Python. You have parameters to select. I'm assuming also in my framework that there's a transmission bandwidth that constrains you to go from 16 kilohertz to 32 kilohertz. So your 3 channels have to fit within that band, and you'll do testing with different spacings on the carrier locations. The tighter they are together, the more bandwidth efficient you are, but then it puts more demands on the filter. So you're going to do a little experiment where you see how relaxing that and having guard bands in between makes things work nicer. But if you were to try to slide this too far away, then it's going to bump against a transmission bandwidth, and I have a filter implemented in the framework that makes the signal start to get taken out by the filter. So from the design standpoint, there's a spectral shaping filter for the speech, and the idea is the speech runs from 300 to 3300 hertz, so it's not really that high a fidelity. It's like audio grade for telephony. I think that's exactly the standard for speech telephony, is 300 to 3300. Because I want you to be able to process this in relatively fast time on the computer, we're going to start with signal samples that are at 8 kilosamples per second. And that's what the speech vectors I've been playing with do. They're at 8 kilosamples per second. But then in order to have a high enough sampling rate to place carriers at a higher frequency, we upsample by a factor of 12, and you'll be working then with, in the radio spectrum sense, with 96 kilosample per second signals. Still audio in a way, not very high a frequency. Actually, this is an audio sampling rate that's used in digital mixing consoles, because we have 48 kilohertz as kind of a standard now. Twice that is 96, and then 4 times that is the, what is that, 1, can't add right now, 2, 18, 19, 192 kilosamples per second. Some people might have digital mixing equipment if you have a home studio to play guitar into and make recordings. So you might, does anybody have that? So you're familiar with these sampling rates probably. So to make this all nice and neat and tidy for working on the project with, I've got in the Jupyter Notebook a top-level transmit and channel function that's pre-written for you in the notebook. So it It allows you to enter in attributes, so there's an interface on here where you get to put in the carrier frequencies as a list, FC1, FC2, and FC3, what modulation type it's going to be, whether it's going to be speech or noise. So that's just a string. And then for testing purposes, I have this M combo, which holds a triple of integers that are either 0 or 1. So 3 ones means all 3 carriers are on. 0, 1, 0 means just the center carrier is on. And this is useful for debugging purposes, where you're going to do different experiments where you're going to keep the neighboring interferers off and only have the center one on, or vice versa. You'll do some experiments. And this is kind of the way you might develop a multi-channel system where you're going to look at superposition effects. So you have a means of turning things on and off. There's some rates that are established in here, like the upsampling factor of 12, the underlying sampling rate of 8,000. And then this is in the framework where there's a Butterworth filter designed out to be a bandpass to shape from 300 to 3300. Generate noise sequences, or if speech is selected, these guys we've been playing with a lot. That's the male US, the female US, and the British male. So those are your 3 messages that you're going to send through. So you'll just have a little bit more fun with that. This code is provided. This is the provided part. And then you load up the cases of what you're going to actually modulate up. So you have to call Weaver, and this is the function you're writing. If I demo it today, and that's my intent, I've got a solution that I've got in my computer. So if you run it in the demo mode, which means you set demo equal to true, you're going to get an error because it's going to go looking for a piece of code that I'm not giving you, because that's the answer. But I'm going to demo it with the answer running. Likewise, there's a demod function that doesn't exist either, because you have to write that. So these are the other pieces in that, the channel, and then finally it superimposes everything, applies another filter, the bandpass filter gets designed and gets applied, and then the output occurs. Imports at the top of the notebook, we're using a bunch of other pieces from scikit dsp-com. We're using optionally, depending upon what you want to use, you're going to do all your code writing in the notebook. So all these imports are already present. I'm importing SIG-sys again. I'm importing FIR design helper, IIR design helper. Those are the 2 types of digital filters you can choose to use. And then I'm importing another module called multi-rate helper. And the documentation for both of these is now held on GitHub. So I moved the documentation over there. And the tool I'm using right now doesn't link us there very easily because it doesn't support hot links. But if you scroll down in here, these are actually hot links that are in a regular PDF viewer, not this tool that I write on. So that'll take you right over there. And it's linked at various places throughout this notebook. It's actually linked at the very end as well. And it's linked right inside the Jupyter Notebook itself. So the Jupyter Notebook has pretty much everything in it. I've tried to get the text all synchronized. There's a few items that are in more detail in here, but I'm going to give you a quick little demo of it. And one of the things I'll want to spend more time on next week is just talking about what interpolation and decimation are all about. But this is the Weaver circuit, and I think everybody now understands how it works, or at least you proved that it worked in the homework problem, right? So this is the DSP-based version of the Weaver circuit. You come in with signal samples instead of a continuous time signal. You produce sinusoids with discrete sampling with samples, index n, and then you design a low-pass digital filter at a cutoff W/2 relative to the sampling rate divided by, well, relative to the sampling rate. and then it gets upsampled in this interpolator function by a factor of 12. So now it's at 96. So when it's, as it says down here, it's 8 kilohertz. All the processing is 8 kilosamples per second to the left of the red line, and then it's upsampled, so it's operating at 96 kilosamples over on this side. And then, of course, you implement this switch, so you can be upper sideband or lower sideband. So the code that you write for Weaver has to support both, even though you're only going to use one mode. You do have a mode switch in it, just like you played with in the homework problem. So that gets discussed in here. Interpolation and decimation gets discussed. The demodulator, I don't think I have a block diagram for it per se, but it's a coherent demodulator, so it's going to bring the signal in. It's going to have to decimate by 12 to take it back to 8 kilosamples, and then the coherent demodulation gets applied. But there's an interesting savings that you can do there in terms of not having to have multiple filters, and that's talked about in the handout, how you can economize, because the downsampler has this neat property that you have to have a low-pass filter in it before you downsample by a factor of 12, and this filter right there can serve as your coherent low-pass filter following coherent demodulation. And then you downsample back to 8 kilosamples so that it's audio speech you can play out and listen to it again. That's the whole point there, so you can listen to it when it comes back out again. And there's objects, custom objects that you're going to use. You're going to use the multi-rate IIR or multi-rate FIR object to create an instance, or the multi-rate IIR class to create an instance that you can then supply filter coefficients to it, which is right here, in a format known as second-order sections, or just a big FIR filter if you choose to go that way. And then there's a method associated with that object that allows you to do a downsampling on a signal vector or array and indicate what factor it should be, 12 in this case. So this is going to introduce you to a little bit of object-oriented, not really programming, but just using objects and methods associated with objects. So I think it'll be also good. Python is now becoming a very, very popular language. I mean, I've done some reading the last few weeks that it's even more popular than I even imagined that it was for data science and so on. And there's surveys out there right now. It's really growing rapidly. And of course, companies are using it a lot too. Maybe you found out about that during the career fair, I don't know. Did anybody talk to anybody about Python when you were talking to anybody? So you do spectral analysis, some other pictures and things. The main meat of it is the project tasks. So I'm going to jump over to the notebook right now. While I'm flying through there, since I know I'm going to run out of time, I'm just going to go back and look at what I'm referring to in the Chapter 3 notebook. Bandpass sampling theory is introduced. I have a function for plotting spectra of signals that have been sampled at whatever rate you want, and it's a little function that allows you to draw the picture of the spectrum and then the images that get created, because this kind of can be daunting. You can do it on your own by hand, but this kind of draws the pictures for you, where you've got to visualize all the translates and how they interleave and superimpose. So I've got some help on that in the Jupyter Notebook. And then PCM and so on, which we'll be talking about next week, is written up in here. The notebook, though, is right here, Project 1, 2018. So run this first cell, and it imports all these things. I bring in a test vector, have the block diagram brought over in here. I have most of all the correct text, but if there's any text that you see in here that's inconsistent, the PDF is the correct. This I'm trying to get synchronized. There's a few little things that I think are probably still not quite right. I tried to put it in there so you could just read this and write code, debug it, and all stay in the Jupyter Notebook. So I have notes. I have top level transmit function. So right here, for the demo purposes, I bring in comproject1_new, which is a version that I fixed up from before for the new scikit package, so I import things properly, and I just import it with its alias solved. So down here, this is the top level function, which I give you. It's complete. You just shift enter and it runs. This is the template where you're going to put your code in to build your Weaver modulator, so it's placeholders in there. This is the template for the SSB DMod, so that's got placeholders in it. You have to abide by the I/O in these functions. And then for basic transceiver testing, here I'm going to put the carriers up at 2,000, 20,000, 24,000, and 28,000. I'm going to do noise testing, and I'm going to say put all three carriers up and run in the demo mode. So here, I'll just run this. The filter design tools are reporting the various orders of filters that it's built to implement the design, just because my filter design functions always report that, and it's kind of nice to see what you're designing. I'm sure you're going to look at this and say, what did Dr. Wicker do for his implementation? You can at least see the order that I got. You won't know the attributes of the filter design exactly, but then I run the DMod right here, and it's got some filters in it too. But you've got lots of opportunity to pick and choose from filter types, and that's what I want you to have, is pick critical frequencies in the design of the filter, and that I go through in the documentation that's on the GitHub site now, that's not embedded here. You have to go find that. So there's the spectrum of one message. It's just band limited noise from 300 to 3,300 hertz. Maybe I'll just run this so you can believe me that it's there. And there are the three signals that have been transmitted up on the three carrier frequencies, just sitting side by side with a noise spectrum. And I come along and run the DMod, which is what has actually been done in here too. Let's see, where was that? Yeah, I run the DMod right here. So there's the demodulated version, not quite as beautiful as the one that was transmitted. Not too exciting, it's just noise, but it's a noise test. But now what I can do over here, and what you'll be doing, is I can change this to speech, and it's going to bring in the three speech vectors. So then when I go look at the outputs, that's one of the speech vectors, spectrum, and there's the speech vectors of all three. Single sideband, so it has more content at low frequencies and less for the high, so that's three superimposed channels. And then down here, here's the spectrum. Let's see, I didn't run something. That was, I guess that's the DMod. That doesn't look right though to me. I didn't. Yeah. There we go. So that's speech. And then do that.
Take the winding path to reach the lake. Note closely the size of the gap.
So that's the one in the middle, I believe, is the female US. And if I was to go up here to the DMod and say I want the signal that's at 2,000, or 20,000, I mean, I would instead pull that signal down. And then if I was to go ahead and do this,
the little tales they tell are false. The door was barred.
and if things are messed up, you're going to hear strange things, like remember when we demodulated single sideband with a carrier frequency not right, it'll be pitched really high or really low, or it'll just be things that are annoying sounding. And everybody's going to have a little bit different experience because you're maybe going to debug differently, and try different things. But what you'll be able to do always as you're developing this is you can go up here to your transmitter and you can, only have one turned on and turn the other off. I'm going to have you do a measurement where you're going to see the crosstalk between the channels that are above and below and how they impact the center channel. We're not hearing that right now, but if you listen carefully or actually do a dB power measurement, you'll see there's a ratio of how many dB down. And it depends a lot on how you design the filters. I really don't want you to go crazy and use really high order filters because that's impractical. I would say go for the best design. If you have a little bit of leakage, a little bit of crosstalk, it won't be that terrible, but it'll be something to play around with. I've got it set up in my scripts where I can obviously tweak things. So, question?
Will we be turning in a report, or will we be just sending in the files?
Okay, I want the report with the code in it, so you can print this off to LaTeX PDF, which many of you have been doing already, just HTML and printing it. So yeah, I do want this so I can grade on it, but then I'll want you to send me the WAV files that you'll write, and those will be submitted too, so I can listen to them. And then thirdly, your Jupyter Notebook. So if there's an issue with something not working at the end, and it's not sounding really good, but it's kind of where you got stuck or something, I'll be able to go back and recreate it in the Jupyter Notebook and just see if I can see something obvious. It's kind of your backup means. But the primary thing will be the printed version with the code cells in it, all the cells filled in, because if I scroll down in here, you can see I've got placeholders for you to answer all the questions and just develop your answer right in the notebook. This was my first really serious go in the Jupyter Notebook about 3.5 years ago of seeing how well it worked. And it works really well, I think. I'm biased though. Some of you are using the Jupyter Notebook a lot now and you're already familiar with how you can write markdown cells and so on. So, and put graphs in it. So that's kind of the plan. You'll have the paper version to grade on, you'll have the WAV files you'll send me, and then in the zip package with the WAV files you'll have your version of the Jupyter Notebook. And when you get ready to start sending WAV files, just don't send them saying project 1. At least have an underscore and have a name on it or a group of names, so that way when I start pouring all the stuff into my student projects folder, I'll have a means of tracking it all out and unpacking it and then working with it from that standpoint. So any reaction right now? Does this seem doable? It's like anything, you got to get into it, start reading it. The homework is not too terribly awful. It's actually kind of like stepping backwards into sampling theory. You're going to be looking at basic sampling theory, and then a little bit of the time division multiplexing starts to show up because I gave a couple problems on that as well. That finishes off chapter 3. No, it's Thursday. We're back to the Thursday schedule. And if things don't work out well, I'll modify it on Tuesday. So.